Let's go over the answers to worksheet 3. Initially, a spring is compressed with the roller coaster cart stationary next to it. The final scenario, the cart is moving at the very top of the loop-de-loop. Assume no friction. So in this position, it's not above the ground, so no GPE. It's not moving, so no KE, but it is compressed, so that's EPE, all elastic potential energy. In the final position, you notice that the cart is off the ground, so we gave it some gravitational potential energy, and it's moving, so we gave it some kinetic energy. Notice that we say the amount of energy in the initial position is equal to the amount of energy in the final position. And that's also what we see with these energy bar graphs. We gave it 4 bars of elastic potential energy. 4 bars. And on the right, we also have 4 bars, but we've split them. 2 kinetic energy and 2 gravitational potential energy. This is the same scenario, but now let's assume the cart is not as high up. So, same as before, elastic potential energy. That elastic potential energy gets transformed into gravitational potential energy, but notice not as much because it's not as high as what it was before, and the rest is kinetic energy. So we have 4 bars of elastic potential energy on the left, so we need 4 bars on the right. 3 of the bars we said were kinetic energy, and 1 of the bars was gravitational potential energy. But the idea is that the law of conservation of energy tells us however much we have in the initial position is how much we have in the final position. So 4 bars and 4 bars. A 20 kilogram cart rolls down a 5 meter tall frictionless hill. How much gravitational potential energy is stored at the top of the hill? Well, to answer these questions, let's first examine the picture and these 2 energy bar graphs. So at the top of the hill, the cart has 0 velocity. It's not moving, so it has no kinetic energy. It's not stretched or compressed, so no elastic potential energy, but it is 5 meters off the ground. So it has gravitational potential energy, 4 bars worth. At the bottom, you notice it's on the ground now, so it has no gravitational potential energy, but it is moving. So all of that gravitational potential energy got converted into kinetic energy. Again, we know that because the cart is moving. So how much GPE is stored at the top of the hill? We have an equation. It's mass times gravity times height. The mass was 20 kilograms. That was given to us. The gravity is, on Earth, always 9.8. And the height is 5 meters. That was also given to us in the problem. Multiply those 3 together, and we know that this cart initially has 980 joules of gravitational potential energy. If no energy is dissipated, how fast is the cart moving at the bottom of the hill? So here's where we have to use the equation for kinetic energy. It says how fast. Kinetic energy has velocity in it, so we're going to be solving for V. We know we have 980 joules of kinetic energy because if we have 980 here, then we have 980 at the end. So 980 joules of kinetic energy equals 1/2 20 times V squared, and that 20, of course, was the mass. So do 0.5 times 20, that's 10. Divide both sides by 10, that's 98, and then take the square root of 98. That gives you a velocity of 9.9 meters per second. A 5 kilogram crate is propelled up a frictionless hill by a tightly coiled spring with a spring constant of 30 Newton meters after compressing the spring 0.8 meters. So here's what we have initially. It has no velocity, so no KE. It's not off the ground, so no GPE, but the spring is compressed, so we have 4 bars of elastic potential energy. In the final position, look, it's above where we started from, so it has some GPE. And the velocity is greater than 0, so it also has some KE. This is how I distributed my bars, but if your proportions are different, that's okay. As long as you have 4 bars on the left and 4 bars on the right, you're okay. How much EPE is stored in the crate? Well, EPE equals 1/2 K. K is the spring constant. It's given to us. It's 30 meters times X. This is how much the spring is stretched or compressed, and it's compressed 0.8 meters. So 0.8 squared times 30 times 0.5 is 9.6 joules. So we have 9.6 joules of stored energy. Part B, if 7.2 joules of the energy are transformed into kinetic energy, how many joules are transformed into GPE? Let's make sure we understand that question. We have 9.6 joules of elastic potential energy. That means we have to have 9.6 joules over here. And part B tells us that 7.2 of those joules is stored as kinetic, so how much is stored as gravitational? Well, that's where we can set up the equation. We know on the left, elastic potential energy equals on the right, kinetic energy plus GPE, and that's what we see at the bottom there. We know the EPE is 9.6. We calculated that in the previous problem. We know that the KE is 7.2, so we can solve for GPE. So the GPE is 2.4 joules.